Hello, you are welcome to the tutorial on dimensional analysis. It's a wonderful time having you to continue this lesson. So far, it's been so interesting, and from the feedback, you are all enjoying the lesson. This is the third lesson in this series on dimensional analysis. Today, the lesson specific objectives will be to look at the importance, otherwise, the application of dimensional analysis. We also take time to look at the limitation as far as dimensional analysis is concerned. Then, out of the importance of the dimensional analysis, we'll focus on the first one, and that will be checking the correctness or the dimensional validity of equations. So that will be the lesson for today. And I want to assure you that we are going to use this as our reference. We took time to look at each of these quantity and eight-dimensional equation in our previous lesson. And that is going to serve as reference for this lesson as well. Now moving on to our lesson objective. Let's first look at the importance or the application of dimensional analysis. So dimensional analysis, for our discussion so far, is used to one, check the correctness or the dimensional validity of an equation. Under this, it means that we will have to examine a lot of equations and see whether dimensionally they are correct or not correct. The second application is dimensional analysis is used to form or create a relationship between physical quantities. Dimensional analysis can also be used to determine the units of physical quantities. So these are the three applications of dimensional analysis. Again, let's look at the limitation as far as the usage of dimensional analysis is concerned. The first limitation is when an equation has a dimensional constant. Dimensional analysis does not give information about that constant. It's just say ignore it. And so all the numbers, dimensional constants, most are ignored in dimensional equation, and that is a limitation. The second limitation is mostly dimensional quantities are derived for quantities that have only three factors, especially those with mass, length, and time. If a quantity depends on more than three, an equation, a formula has 4, 5, and more terms, it cannot be derived with dimensional analysis. So the maximum it can is 3. This is for your jurisdiction as in the senior high school. But it can be a different story as you climb the academic ladder. And the last of the limitation is when an equation contains trigonometric functions as well as logarithmic functions, it cannot be derived with dimensional analysis. Simply, trigonometric functions, logarithmic functions are ignored in dimensional analysis. And so this is the limitation that dimensional analysis has. Now let's focus our attention on the importance of the dimensional analysis by looking at the first one that talks about checking the validity of an equation. So we are going to use this to check the dimensional validity of few equations which we will select for this course. And I'll leave you with some assignments as well. But I want you to understand that in order to check for the correctness and the dimensional validity of an equation, a principle is used. And that principle is called the principle of homogeneity. Friends, by this principle of homogeneity, it simply states that you can only say an equation is dimensionally valid if and only if the dimensions at both sides of the equations are the same, exactly the same. That is, for any equation, there is a left-hand side of the equation and the right-hand side. So if the dimension on the left-hand side and that on the right-hand side are the same, then that equation is dimensionally valid. Otherwise, you can then say an equation is dimensionally invalid if the dimensions that are situated at both sides of the equation differ. They are not the same. That is, if the left-hand side of the equation has a dimension which is totally different from that of the right-hand side, that equation is invalid and otherwise incorrect. So that is the principle that will guide us as far as today's lesson is concerned. Friends, let's take a note here that the validity or the invalidity of an equation can only be checked if and only if the physical quantities of the equation whose correctness we want to check are expressed in their dimension. What this statement simply means is that you cannot just look at the equation and simply say it is valid or invalid. You need to go an extra mile, and that is express each physical quantity in that equation in their dimensional form. So as a way of illustrating, let's say you have force expressed as mass times acceleration. In the equation form, we write F is equal to ma. Looking at this, you can't be sure whether it is valid or invalid. And so the surest way to check the validity or the invalidity is to express each physical term here in your dimension. So for the force, a dimension is mlt exponent negative 2. Whereas for the mass, it's a capital M times the acceleration, which is lt exponent negative 2. So this is the left hand side of the equation, and that is the right hand side of the equation. When you multiply the right hand side, you end up getting mlt exponent negative 2. And a quick inspection of what we have tells that this equation has both quantity expressed to be the same on the left hand side and the right hand side. So I can then be sure to say this equation is valid with the conclusion that the left hand side has quantities equal the right hand side. So that is what we'll be doing throughout this lesson. Thank you very much. And so I'll be switching over from this presentation board to the writing board. Then we'll take some series of questions and check their validity and their invalidity. Great. Thank you for staying while I was flipping over. Let me be quick to add that this is going to be our reference material. Kindly take time to know every dimensional equation to every physical quantity expressed here. We will be using this as reference, and so take good note of them. Let's start from question number 1. And the preamble goes like, check whether or not the following equations are dimensionally valid or invalid. And question number 1, the equation is v equals u plus at, where v equal to final velocity U, initial velocity, A, acceleration due to gravity, and T equals time. Great. So every term in the equation has been defined. Our task will only be to substitute them. So the first thing you do is the equation is V equals U plus 80. Let's look at the various terms. This V has been explained to be the final velocity, and so it is velocity. Velocity has its dimensional equation as LT minus 1. So we just quote it like that, LT minus 1. The second term there is the dimension of the U, and the U is equal to initial velocity. It is also a velocity, and so LT minus 1. The next of the term is the A, which is the acceleration. Now, acceleration is LT minus 2. And that is what we also quote. Then the last of the term is the dimension of T, that is time. And it is given as a capital T. The next step is, after expanding these various terms in their dimensional equation, let's substitute into the equation. For the V, I will write LT minus 1 equal to, for the U, also LT minus 1 plus the A, which is LT minus 2 multiplied by the T, a capital T. Don't forget to keep this in brackets because the A is multiplying the T, while both are added to the other terms. So the left hand side of the equation still maintains LT minus 1 equal to LT minus 1 plus, this is a multiplication. The T has an exponent of positive 1. So L by 1 in front of the T still gives L, but there is a T with negative 2 multiplying a T with exponent positive 1. Per the rules of indices, you will write one of the bases, then add the exponents. That will be minus 2 plus 1. So we repeat the same equation like that, plus LT. Negative 2 plus 1 is a negative 1. Looking at the equation critically, the left hand side still goes as LT minus 1 equal to, these two terms on the right hand side are the same. And so when added, you have 2 L2 exponent minus 1. Friends, don't forget something here. When we looked at lesson number 2, we said numbers, rational or irrational, are dimensionless. So in this our context here, the 2 here is said to be dimensionless. Simply, it has to be ignored in this equation. And when that is done, we'll be left with LT minus 1 on the left hand side, and it's equal to LT minus 1 on the right hand side. So by this inspection, you could confidently state that since the quantity on the left hand side is exactly the same as the right hand side, the equation V equal U plus AT is dimensionally valid. So this is how we check the validity of equation. This is the first of the examples, and I trust that you have followed, you have grasped the concept. Let's proceed to question number 2. Question 2, under the same preamble, we have the equation F equals mg plus v, where F is the force, m mass, g acceleration due to gravity, and v final velocity. So F equal to mg plus v. Looking at the various terms, the dimension of the F, which is said to be force, could be written as m l t exponent minus 2 as a reference. So with time, we will not be referring. I think you will be used to it. For now, because I'm teaching, I want to be very quick with it. Great. So m l t minus 2 for the force. For the next one, we have m, that is the mass. Its dimensional equation is a capital M. Great. That of the g is the acceleration due to gravity. Earlier we quoted it as LT minus 2. Then the last is the v, the final velocity, which is a velocity. So LT minus 1. Our task now is to substitute the dimensional equation into the given equation. For the force, we'll have m LT minus 2 equal to the product of mass, capital M, times the g, which is LT minus 2, plus that of the v, LT minus 1. Okay, so multiplying the other side, this will be MLT minus 2 plus LT minus 1. Looking at this, there isn't any way you could add these two terms because they are unlike. Therefore, by inspection, you can say that the left hand side is totally different from the right hand side. I mean the expressions there. And so you are correct to say the equation F equals mg plus v is dimensionally invalid or incorrect. Thank you. Now, question number 3. S equals ut plus half at squared, where the S is equal to displacement, u initial velocity, a acceleration due to gravity, and t time. Great. As done, equation is S equals ut plus half of at squared. We need to express each of these terms in their dimensional form. The first is the S, which is said to be displacement. Displacement is a length, and so it has a dimensional equation to be L. Secondly, the U, called the initial velocity, is LT negative 1. This T is a capital T in terms of dimensional equation. The A, acceleration due to gravity or acceleration, LT minus 2. Great. Now we need to just substitute into the equation as they appear. For the S, it will go for L equal to U, that is LT minus 1 multiplied by T. The T has exponent 1 plus half of at squared The A is L t minus 2 multiplied by t squared, the capital T and a square, all multiplied by half. Great. The left hand side still maintains the L equals, now multiplying u times t, that is LT negative 1 times t exponent 1, it will be that the L will be maintained, but the t will be multiplied, and the exponent will be added. Per the rules of indices, negative 1 plus 1 is 0. So that will be t exponent 0 plus half. Here, the L will be maintained. Then t exponent negative 2 times t exponent 2 will also be t exponent 0, since negative 2 plus 2 is 0. If you continue, the left hand side still maintains the negative. Now t exponent 0 equals 1. So don't forget that t exponent 0 is equal to 1. And that will remain as L plus half L. Now, with our understanding that numbers, whether rational or irrational, are dimensionless, you could simply say that this half is dimensionless because it is a number. Okay, so let's keep that in mind. And that will bring us into getting L equals L plus L. Then the L plus L will give you 2L. Again, this 2 is dimensionless. And so the answer will now be equal to L equals L. By quick inspection, you could easily tell that the dimension or the quantity on the left hand side is equal to the quantity on the right hand side. And so you can say on authority that the equation is dimensionally valid. Thank you. Question number 4. The equation is t equals 2 pi square root of rho h over g, where t is for period, the rho for density, h for height, and the g for acceleration due to gravity. Now with that equation, that is t equals 2 pi square root of rho h over g, we need to substitute the dimensional equation for each term there, starting with that of the t. This t is called period. Period is a time, and so the dimensional equation is t. That's a dimensional symbol as well. Remember that the 2 pi is dimensionless in that 2 is a number. The pi, which is the Archimedes constant or Archimedes number, is also dimensionless, and so they are ignored. The next term to consider is the rho, which is density, mass over volume. Its dimensional formula or equation is m L exponent minus 3. That of the h, the height. H expresses, or height expresses, length, and so it is L in terms of dimensional symbol. Then lastly, the g, acceleration due to gravity. So it is acceleration, LT exponent minus 2. We now have the luxury to substitute this into the equation. So for t, it still remains as t is equal to 2 pi ignored, then square root of that of the rho m L exponent minus 3 times the height L, all these over the g, m L exponent minus 2. Okay, so let's work on those under the square root. For the numerator, the m multiplies a 1 in front of the m, L, so that will become m. M has got no counterpart here, so it is m. But the L here is exponent 1. And per the rules of indices, while these bases are multiplying, 1 is maintained. The exponents are added, so negative 3 plus 1 is a negative 2. All over m L exponent minus 2. So this is what we are faced with. Looking at this, the t is equal to the square root of all these terms are the same, and so they can easily cross out. The m goes with the m, L to the power negative 2 goes with L to the power negative 2. Okay, so when that is understood, easily that will give us square root of 1. And the square root of 1 is 1. Just look at the equation. What is on the left hand side and what is on the right hand side are not the same. And so, by a quick checking of the terms, you will be correct to say that this equation is dimensionally invalid, since the left hand side is not equal to the terms on the right hand side. We will take a break with this lesson for a minute, then we will continue. Okay, so welcome from the break. Now let's continue with question number 5, which reads as v equals square root of t over mu, where the v is for velocity of sound in a stretched string, the t is tension in the string, and the mu is linear density of a string. So that is the equation. V equals square root of t over mu. It is now prudent that we look at each of the parameter there. The velocity of sound in a stretched string is still velocity. So it has the dimensional equation as LT exponent minus 1. The T is said to be a tension, and tension is a type of force. And the dimensional equation for force is ml T exponent minus 2. Then that of the linear density, also called mass per unit length, can be said to be ml exponent negative 1 from our reference. Okay, now substituting this into the equation, that of the v will become lt minus 1 equals the square root of the t m lt exponent minus 2 all over that of the mu m L exponent negative 1. The left-hand side still maintains as LT negative 1 equals square root of. If you look at it critically, I think the m can cancel the m. Okay, let's do it by indices. So you will have it as m LT exponent minus 2 times. Then you have to rewrite this in a linear form. So they will come up and join what is on the numerator. What happens is that they will be negated, the exponent. So m travels up. The power was positive 1 down. It will go to become negative 1. The L is negative 1. It will become positive 1. That's why I said negated. When you negate a negative, it's positive. When you negate a positive, it is negative. That will be LT exponent minus 1 equal to the square root of. Now m by m carries a positive 1. So that will be m exponent 0 when the exponents are added. Then with the L is positive 1 and negative, positive 1 on both sides. And so the exponent will be added to get positive 2. Then t could be written as negative 2. Remember that the m exponent 0 is equal to 1. It still remains at LT exponent negative 1 equals L to the power 2 t to the power minus 2 all to the power half. This is mathematics. The square root of a number is the same as the number to the power half. This half multiplies the power. The exponent of each term here, that will be LT to the power negative 1 equals L to the power 2 times half t to the power minus 2 also times half. So LT to the power negative 1. Now 2 times half is 1. Then negative 2 times half is negative 1. And so by quick inspection, you can stamp on authority that the left-hand side is equal to the right-hand side. And so the equation V equals square root of tension over linear density is dimensionally correct and valid as well. Now, question number 6 and the last question in this series. The equation is F equals 1 over 2L square root of T over M over L, where the F is the fundamental frequency, the L is the length, the T is the tension, the M is the mass, but M over L is the mass per unit length. So they are together. Great. That's from the equation. Let's look at the dimensional formula for each of them. The first is the fundamental frequency. And from our reference, frequency is having the dimensional equation as T exponent negative 1. Good. That of the L, which is said to be length, will have it as capital L. The T, which represents tension, is a force. So it has M L T exponent minus 2. Then the next one is mass per unit length. Mass per unit length. This is the same as the linear density. So it is like you're saying mass exponent, that is mass L exponent negative 1. So these are the terms for R. Let's substitute into the equation. For the frequency, that will be T exponent negative 1 equal to 1 over 2L. Then the square root of the tension MLT minus 2. Then all of this over the mass per unit length ML exponent negative 1. Great. Now take this for me. The half here is dimensionless, as already agreed on. So we could go ahead and write it as T exponent negative 1 equals 1 over L. The 2 is gone. Then the square root of, for this, if you should write it in a linear form, the M will automatically cancel out the M. But let's do so. So you have M. Great. For the numerator, M L T minus 2. Then the denominator goes up, but the powers are negated. So M becomes negative 1. The L becomes positive 1. Great. So T exponent negative 1. This will also go up as L exponent negative 1. Then square root of the M multiplied by the M. This has got a power of 1. So 1 plus negative 1 is 0. This is L, the power of 1. Another L with the power of 1. Exponent added, you have 2. Then T, exponent of negative 2 against nothing. So you're going to get negative 2. Thanks. So L, T exponent negative 1 because L exponent negative 1 square root of L square T negative 2 because M to the power 0 is 1. As earlier established, this will mean that you take each of these terms to the power half. Great. So half of 2 is 1. So this one will give us L. Half of T for negative 2 is T negative 1. So T exponent negative 1. When this is multiplied, the L has got a power of 1. So L negative 1 plus negative positive 1 is 0. Then T negative 1. Don't forget that L to the power 0 is equal to 1. So looking at the equation, on the left hand side you have T exponent negative 1 and it's equal to the right hand side T exponent negative 1. Therefore, by a quick inspection, you are right to say that since the left hand side is equal to the right hand side, this equation is also dimensionally valid. Thank you very much. Stay blessed. And the next questions will be for you to try. God bless you very much.